Hello. Welcome again to another section of Bed Talks here. So this video is actually going to be kind of wrapping up kind of the big end to Calculus 3 here. And think about what we've kind of discussed and bring everything together. Basically everything that we have learned coming from this entire last couple of months, kind of culminating in this theorem, and kind of trying to figure out, where do we go from here? In some way, like why did we have to go through this whole process, right? Why did we get to this point? What are we really talking about? And I'll at least tell you something really quickly before we get this started. When I took Calculus 3 back in undergrad, one really interesting thing. So at the end of this all, I finally felt, once I learned the divergence theorem, I finally felt that I was in such a place where it would take me a really long time to kind of explain to somebody, how do we get to here? Like, all the steps needed to get to this point. It seems very, very simple at this point because we've already gained all this material, but I really finally internalized how math is so integral, for lack of a better word, for that fun play, and how crazy we've kind of had to step this entire thing up going forward. How we have had to basically build everything and grapple with everything kind of going from here. So in this talk, the divergence theorem is going to basically give us a way in order to solve this integral that we were talking about for the last couple of weeks. It's kind of this flux integral. How much fluid is going through a surface, right? How fast is it going through? How much fluid over a certain period of time is it going through? Is it going in? Is it going out of that surface? And so on. And what this, we have seen here that we can calculate this by, parameterizing our surface, and calculating this with RU cross RV, even similar to what we did just in the Stokes theorem, right? Very similarly, we parameterize our surface with R of UV, we calculate our normal vector RU cross RV, and then we can calculate this whole thing out. But this is actually a very taxing technique. And if we just have a regular surface S, it might be that this is the only way we really can do it. Genuinely, it might be that we have to just go through this process. We might have to parameterize. We have to go through this. But there's going to be a really, really specific case that we're going to talk about now. And this specific case actually happens very, very often, and kind of it comes from a lot of different places. So let's assume S is completely bounded. It bounds a volume, and we'll call this V. So you can imagine that I take a whole surface here, and this surface actually bounds a volume, any volume. So take this, right? Take this bottle. Let's assume my surface S is this entire cylinder. Maybe even this, maybe my antibacterial wipes. My surface S is this entire cylinder, the entire thing, my surface. And I want to try to find out how much fluid is moving through my surface. All these points, like I have this fluid, right, kind of pushing in these different directions. How much is flowing through every single part? And kind of think about the flux of that. But now I'm thinking about this something as a closed, this is a closed surface. Okay, this is a closed surface now. So if I'm trying to think about this as a closed surface, one thing I now need to think about doing is how can I utilize it to my advantage, right? In the last talk we kind of just did, we saw we had a closed loop, right? Stokes theorem, we had a closed loop, and we utilized to our advantage by using Green's theorem or Stokes theorem to think about, I can maybe, transform this to maybe an area integral on some sort, right? Transform that work integral to an area integral or a line integral into that. And one thing in that case too is we were relating the boundary of a surface to the surface itself. That's what we're going to do here. But the first thing I'm going to do is I'm going to introduce something else to you here called the divergence of a vector field. We need this mainly because of this word divergence, but there's a really, really interesting part to this. So we call this the divergence. We sometimes note this as div of f. We also can note this as a dot product between the gradient operator, which is this operator here, and my vector field f. And this is going to be a scalar quantity, where this is actually the derivative of my x component with respect to x, plus the derivative of the y component with respect to y, plus the derivative of the r component with respect to z. And this right here is the divergence. We will call this the divergence of a vector field f. And what does this tell us? So a couple of really, really interesting things. It tells us, well, the divergence has a, what is the name divergence really saying? Well, it's the divergent. What is divergent here? So how divergent is the vector field? So what do we mean by that? Well, there's three possibilities. It could be positive, it could be negative, or it can be zero. Right? That's kind of what this is saying. So if this vector field is divergent at a specific point, we calculate the divergence at a specific point. Px plus qy plus rz is greater than 0 here. If we say that this is specifically some value that is positive, how can we now utilize this, right? What can this actually mean? Well, this means specifically that things are diverging away from that point. So fluid is moving out of a point, is moving out. So you kind of think about this as fluid is moving out of this point here. It's moving directly out in this case. And
so the fluid is moving out, we say that it's diverging away from a point. So you can kind of imagine, we can kind of think about this as we call this a source. So things are moving away from this point, and things aren't coming in as fast. So some fluid might be coming in, some fluid might be going out. Kind of think about this. If I'm pushing fluid in, we say that the divergence is positive. If more fluid is leaving the surface, more fluid is leaving the surface rather than coming in. That's what that means. If it's negative, we say fluid is moving in. Is moving in. So we call this a source up here, and we call this a sink. That means that more fluid is moving into the surface rather than out of it. And lastly here, if it's 0, we say that fluid is equally moving in. Equally moving in and out. And what's really, really interesting is if we find that the divergence of F is always 0. If it's always 0, this is called, we call that F an incompressible fluid. That's a really weird name of it. So water, for instance, is an incompressible fluid. What that means is the amount of water going into a point is the same as every water going out of that point. So not any single point, is every single point here has the same amount of fluid moving in and out. Now, some things that are not incompressible, or we call them compressible fluids, are these something that where this is sometimes positive or sometimes negative. We actually have some other examples of this. For instance, ketchup, and actually blood is compressible fluid. Fluids can get that. Air is sometimes compressible or incompressible depending on where you are, especially near a wing of an airplane. It can be an actually compressible fluid. Call that. So, the divergence being 0, divergence-free systems are really, really helpful, and they make a lot of fluid calculations easier, but they're not always necessarily physical. Some of them are incompressible, some of them are not. And so that's another part for that time being, but this is at least talking about. So this is telling us, this gives us a quantity that tells us how much a fluid is moving into a surface or out, how much is it diverging, right? You can think about it that way. That's why we have the word divergent. So with this in mind then, how can we utilize this to our advantage? When we're thinking about how do we calculate the amount of fluid that is moving in and out, right? Maybe we can convert this instead to something with the divergence of F instead of that. And this is where it actually comes out to. And the divergence theorem says the following. We can calculate this. There's not many, what's great about the divergence theorem, is there's not that many conditions that you necessarily need to satisfy to kind of check it. Everything just has to be continuous, and you have to have a bounded domain and an outward normal. And this is actually the really important thing too. So the couple of things you do need, F must be continuous. We must have that the normal vector is the outward normal. What do I mean by outward normal? Well, the normal vector that I'm considering here must be pointing outwards and not into the body, not into the surface. We say that F is closed and bounds a volume, I'll call this E. Okay, so I'm going to call, let me just kind of go from here. I'm going to call this entire surface F. It is completely bounded. We need a completely bounded. We can't use the divergence theorem without it. And then what we do is it bounds a volume E. the volume is inside, the cylinder is the volume E, and we have to have this outward normal. So I have to use this normal vector instead of the normal vector pointing in. Okay, and if I have all of this, we can utilize the divergence theorem, which says that this integral becomes just the triple integral over my volume E now of the divergence of f dv. The divergence of f is some scalar quantity. And this right here is the divergence theorem. You could also see this written as at least something that I usually see in my field of work. We usually use this notation here, which denotes the divergence, as I've kind of mentioned up here. So what does this say, just in general? Well, this says that if I want to compute the amount of fluid moving through an object surface here, which is kind of the flux, how much is it moving through a surface? If it's completely bounded, it's related to just figuring out how much fluid is inside of it. How is the fluid moving in and out of every point inside of my volume that I'm being bounded by? And with this nice physical interpretation, this is the divergence theorem here. Now, I just want to show you, this is a really, really easy, it seems like a very nice, easy equation here, but think about how much you had needed to know to get up to this point. You didn't know, first off, what this integral really means. You have to know what a vector field is. You have to know what a dot product is. You have to know what a differential is. What do I mean by a double integral? What do I mean by a triple integral? What do I mean by this dv here? What do I mean by that divergence? Knowing the partial derivatives. I mean, there's so much that you had to have known, going back to even the basic stuff, like what is a dot product, right? What does all this mean? And so this was kind of the first hit for me when I first realized that. It was kind of like, wow, there's a lot of stuff here. But this divergence theorem is super, super, super helpful, because a lot of times triple integrals are so much easier than calculating this. Because a lot of times we have to go through this full process here, right? Parameterizing this and all of that. I don't have to go through it here. I can just, work with my chapter 15 stuff and just find triple integrals, which becomes a lot simpler a lot of times. And the divergence can really be quick occasionally. And we see here the amount of fluid, if the divergence is 0, if we have an incompressible fluid, this will always be 0, which makes sense because we have the equal amounts going in and out. So it should make sense. Okay. So let's do some problems. I'm going to show you how to use this here. I'm going to move it down here, and I am going to kind of work with that right here. So I have a problem here. We're going to tackle this really quickly. Yeah, let's do this one. So I have a vector field f here, which is 2x to the third plus y to the third, y to the z, y to the third plus z to the third, and 3y squared z, where s is the surface bounded by the paraboloid z equals 1 minus x squared minus y squared and the xy plane. Okay, and I want to calculate f dot ds over this surface f. Okay, so I have this. And let's again try to just draw this out. It's really important that you draw this out. We have to make sure we satisfy all these nice conditions here. So if I draw this out, I have this paraboloid kind of coming from up here, kind of come down like this. This is 1 minus x squared minus y squared, kind of like that here. And I'm bounded. My surface f then is this surface right here and the surface above it. Now it's really important that we see here it's both the top part of the paraboloid as well as this bottom part. So think about what you would have to do to evaluate this. You would have to actually do two integrals because I have two surfaces that I need to add together. So I would have to add together the portion that's on my parabola. I would also need to add the portion that is on my bottom here. I have to do both of those. It's going to be pretty taxing, honestly. It'll be really, really complicated, generally. And this vector field is not the easiest. We have y to the third, z to the third. I mean, you would have to probably parameterize this top thing, right, with a, if I have 1 minus x squared minus y squared, probably with thetas and r's. So you'd have sine to the third, y to the, I mean, it would just be brutal, genuinely. So, maybe we should utilize something else. So we have a couple of things. First off, we have this entire surface that's bounded and encloses the domain. Secondly, we have a vector field that's always continuous because it's all polynomial. And thirdly, we can assume that we have an outward normal here. It doesn't really tell us, but let's assume we have an outward normal because we always have to. And so this means that I can utilize the divergence theorem, which says then that this domain E that's inside of here is just the triple integral of E with the divergence of f dv, something like that. So with this case here, what we have to do to evaluate any of these integrals, the first thing you would want to do is calculate the divergence of f. Let's see what that would look like, the divergence of f here. So again, the divergence of f is going to be something like px plus qy plus rz, which is the first component with respect to x, the second component with respect to y, the third component with respect to z. This first component with respect to x here is just going to be 6x squared. 6x squared, right? Because the y third goes away. The qx here becomes just 3y squared. And rz here becomes 3y squared. Or more specifically, this would be 6x squared plus 6y squared. Maybe 6 times x squared plus y squared. However you want to write it. This is the divergence of f. We see this is non-zero, so this is a vector field that's not incompressible everywhere, right? We're going to have some different fluid moving in and out. You know, we see this actually always going to be positive, right? It's actually always going to be positive. So because it's always positive, we should expect that this is actually going to always be diverging away. So everything's a source here. Everything's going to be pushing away. It's going to go faster and faster and faster. Kind of interesting. So if I now want to utilize this, I have this now will become, this integral now becomes the integral over my domain E of 6 times x squared plus y squared dv, where this E here is my domain here, which is just bounded by the paraboloid in the xy plane. And so I now know that I can find the limits of this integral very quickly, right? I know here also that I have this x squared plus y squared, so I might want to use cylindrical coordinates. And so let's utilize cylindrical coordinates here then. So as a reminder, cylindrical coordinates are z, r, and theta. And so we go through the domain. What's the first thing I always hit? The first thing I always hit is the bottom part, which is just 0. Z here and the top part is going to be this 1 minus x squared minus y squared, right? That's where I'm always exiting. I'm always exiting from the paraboloid. If I'm going to make this cylindrical coordinate, this x squared plus y minus y squared has to be turned into an r squared. So here, this becomes an r squared. And now what we do to find r and theta is we project onto the xy plane, and we get this circle of radius 1. And how do we know that we get a circle of radius 1? Because we look up here, when z is equal to 0, this becomes 0 is equal to 1 minus x squared minus y squared. And so I move this over, I get x squared plus y squared equal to 1. And so this is a full circle here. So I just get r from 0 to 1, and theta from 0 to 2 pi. And from here, we could set up this integral up. I have to remember that I have to exchange this for r squared. And in this case, we do have to pay the price and do r dz dr d theta. And the reason why we do it here is we're not parameterizing our surface, right? We're not parameterizing our surface. We don't already have that inherently in this, right? We don't have that. So this becomes then the integral from 0 to 1 minus r squared, 0 to 1, and 0 to 2 pi of 6r squared. I then have to multiply by r dz dr d theta. And this is the integral. I mean, just think about how easy this now becomes. I mean, genuinely, because it will be such a taxing process, a very, very lengthy and long process. You can do it, just such a long process. And you would have to deal with trig subs. You would have to deal with, evaluating sine to the third, y to the, I mean, it was just terrible. So with this in mind now, we can now evaluate this. And this becomes actually a very, very nice calculation. We first integrate this with respect to z, but there's nothing with respect to z. So this becomes just 6r to the third, 1 minus r squared, dr d theta. We can separate these two integrals. And this becomes, I'll just move the 6 out. We don't need that anymore. This becomes here, r to the third minus r to the fifth, dr. This integral then becomes 2 pi. This one right here will become r to the fourth over 4 minus r to the sixth over 6, evaluated between 0 and 1. And so we get 12 pi times 1/4 minus 1/6. So we get here. If I move this 12 through, right, we can get that this is going to be 3, and this is going to be 2. So this becomes 1. So this becomes just pi. And that's my answer. And so I just want to kind of point out here that, think about how quick this just became. Why did we go about doing this, right? What is the reason why we do these kinds of things, right? Why are we thinking about doing this? Well, the reason why we do this is it becomes a very difficult process. We have a lot of different parts, right? If we have a lot of different types of surfaces that are bounding a domain, it can be a lot easier to think about just what's enclosing it rather than the boundary itself. Sometimes it might not be beneficial to go to this process. It might make this more taxing. Maybe the volume is really difficult, and maybe you have a really nice parameterization for your surface. That's totally okay. You can utilize that. But this process here to exchange from a surface to a volume like this is genuinely just incredibly helpful in many different cases. So again, what we do, and this is the process I would suggest doing, is calculate the divergence of F. Make sure you have your domain is completely bounded. If it's not, you can't use it. And then from that, you use the divergence of F, calculate it out, and then just set up your limits of integration as you would for any triple integral. In this case, it's going to be a lot easier to utilize cylindrical coordinates, and note it because we had the x squared plus y squared. And so, one thing I want to now do is show you another really, really quick way of doing it, and another process, and one of the other reasons why this becomes just so incredibly helpful. So let's assume now that I want to calculate the double integral of f dot ds, where f here is equal to z, y, x, something like this. And then I also have that E is the ball, I have that the surface F is the ball x squared plus y squared plus z squared is equal to 16. I want to calculate this integral. So again, this surface here is this ball of, I'm very bad at drawing a sphere right now, but it's this ball of radius 4, right? This is the radius 4. And what would I have to do if I was trying to evaluate this integral? Right? What would I have to do? Just kind of going through the whole process. I'm not going to go through it all, but just think about what you would have to do. If I want to go through the parameterization process, the best way to explain this surface is probably using spherical coordinates, right? It definitely is. You would let x be equal to, right? You would let x be equal to, 4 cosine of theta sine of phi. You would let y be equal to 4 sine of theta sine of phi, and then let z be equal to 4 cosine of phi. And then from there, you would have to then find the normal vector to this by taking the cross product of the derivative with respect to theta with respect to phi. And then you have to plug in these guys, take dot products here. It's just too complicated of a process. And you could do it that way. It's just very long and very taxing. It really is. So let's assume then that I now know that this is a surface. Right? I know this is a surface here that is completely bounded. It bounds a domain. It bounds this volume E inside, which is just the ball inside of it. Right? I have this ball here. The surface is the world outside, and E here is the core of the Earth, kind of the inside of it all. And so if I want to now evaluate this, I'll let the surface be here. What we again do, I can then utilize the divergence theorem and make this the divergence of F dot dv, not dot at all. It's just the divergence of F. And so let's take the divergence of F then. What is the divergence here? Well, if I take the divergence, this just becomes, again, px plus qy plus rz. The derivative of this with respect to x is 0. The derivative of this with respect to y is 1. The derivative of r with respect to z is 0. And so the divergence is just 1. It's a constant. It's just a constant. So this then becomes the triple integral E1 dv. And what does this mean? If I have a 1 in my integral right there, that's just the volume of E. That's it. If there's a constant here, right, it would just be whatever that constant is times the volume of E in that case. So what's the volume of E? Well, the volume of a ball is just 4/3 pi r to the third, right? So it would just be 4/3 times pi. We know that the radius here is 4, which is 4 to the third, which is just 256 pi over 3. And we're done. No spherical coordinates necessary, no calculating the cross product, no calculating anything like that, and we're done. And that's why the divergence theorem is so powerful, because it allows us to calculate the amount of fluid going through an object and convert it, and actually make it, I mean, when we take derivatives, it will make it simpler most of the time, right? When we're taking derivatives, it kind of simplifies things. So taking derivatives is going to simplify it. And if we take derivatives and add them together, right, this is kind of the beautiful thing, where it simplifies it down to almost just geometry here. And that's what's so cool about the divergence theorem, it really is. And I also use this a lot. I know that some other students in research have used this too. I mean, it's a really, really cool thing to be able to simplify a problem down to this really, really, sometimes even trivial calculation like this. So with that in mind, I want to know, that's really it from the divergence theorem here. It really just simplifies the problem down. And now I want to kind of tackle, just kind of thinking about this holistically, right? What is the point of calculus here, right? What is the point of calculus? Well, I would first like to argue this, kind of just coming back to here. And this is something that's brought up in the textbook, and I think is really, really, a really, really good point to make. And also something that, you know, why do we do calculus just in general? And what is the point of calculus here? Let's go all the way back to the fundamental theorem of calculus. Fundamental theorem of calculus. What did that say? Well, that said that if I have an integral from a to b of f prime of x dx, right, it is just equal to f of b minus f of a. So what is this actually saying again, right? If I have some integral here, right, and I wanted to find out, you know, the integral over f prime of x dx, it's just again thinking about the integral here is relating a derivative to the boundary, because b and a are really the boundary. What's the function value at the boundary, right? Kind of relating the boundaries of the original function to an integral with derivative, right, over my interval here. I have a boundary, which is just b and a. In this case, right, this might be a and this might be b. I'm just calculating what's happening at those boundaries, right? Evaluating them as a function and kind of coming back to that. So we have that now. Then, you know, what we saw was we had the fundamental theorem of line integrals, which said something actually really nice too, right? The fundamental theorem of line integrals, what did that say? Well, that said that if I'm over a curve C, and I notice that this could be written as, you know, some potential function. If I have this weird thing that's kind of related to derivatives, right, over my curve C, I can again ignore the curve and worry about my endpoints. Think about the boundary of my curve, right? I could say that this is just r at b minus c at r at a, right? Again, relating back to this. It's very, very similar. Right? We have the derivative, relating some derivative to the over my entire curve to, in this case, the boundary of the curve, which is just the endpoint. And thinking about this, the original function, so relating the derivative to the boundary. And then what do we see in this chapter, right? Kind of relating that exact thing. We had Green's theorem was really the first thing. What did Green's theorem say? Well, again, I'm just gonna write this out. There's more form to kind of draw this picture. And again, here we have this curve C going in this direction, curve C, and this is maybe R at A, and this is R at B. That's what we saw. Again, we could just ignore what's happening in the middle of it and just evaluate something at the endpoint, relating that. Green's theorem then said, what did Green's theorem say? Well, this Green's theorem said, if I want to evaluate f dot dr, and I know I have a closed curve C, let's say I have a closed curve, or maybe I could think about this p dx plus q dy, whatever you want to think about. I could then relate it to some derivatives, qx minus py dA, over my domain here specifically. So I have this domain here. I have this now curve. This curve is positively oriented. And I'm relating again derivatives here to my curve. I'm relating my boundary to my domain. It's kind of a little bit backwards. I've written this here. You might want to think about flipping these two things if you want to do that. But this is the boundary of my domain. Boundary of my domain with no derivative, the interior of my domain with derivative. And thinking about that direction, we can change the boundary to the inside by just taking derivatives. So when I go into the inside, I should be thinking about derivatives more, right? If I go to the outside, I'm just thinking about just generally not really any derivatives. I'm just thinking about just an evaluating of some function here. Stokes theorem. It's again, I mean, I'm going to write it this way now, just so we can kind of see that this process here. The curl of f dot df is equal to this work integral again here. And again, we see that this curl of f, as a reminder, right, is related to the derivatives of my function, right, and it's related to the Green's theorem. Right now, I have some surface here. I have some domain. So my surface now, you know, is this surface here. I have my curve C. My surface S is up here. And again, what I'm doing is I'm relating the boundary of my surface, and I'm relating the interior of my surface. Again, the interior of the surface has always the derivatives in it. And the boundary of it has just the evaluation of the function in this case. Right, this is another way we can kind of visualize this here. And lastly, divergence theorem. As you can see, you can probably imagine that this is going to be the same thing. The divergence theorem here. And the divergence theorem says if I want to figure out the amount of fluid going through an object or going through a surface that's completely closed and bounded, we can relate this now to the divergence of f dv. And again, and again, and again. We have derivatives over here with the interior of my surface, of the interior of this boundary. Again, we are taking something on the boundary, taking derivatives to think about what's happening on the inside. So really, it's saying something like along the lines of if I have the boundary, I'm relating the boundary here to the interior, which is again kind of taking derivatives. And if I want to go backwards, right, just thinking about integrals here. So if I want to think about my going from the boundary to the interior, I want to take derivatives, right? Because I'm thinking about that I have this, I take derivatives, I get to my inside here. I think about, but if I want to go from interior to the boundary, I'm thinking about more about taking integrals and kind of moving up in that direction. And this whole concept of derivatives and integrals is really interesting and kind of relating the interior of something and the boundary of that interior. And that's really what calculus is all about. And this is kind of the story map of what calculus really is, thinking about the relationships between boundaries and the interiors here. So yeah, that's kind of the idea of divergence theorem and really the idea of calculus in general. I mean, there's many different subsets of calculus, which is really important, but you know, the things that you should really think about just in general are kind of trying to figure out these patterns. And these patterns have a really, really clear message that there are ways to correct and connect, or just to connect the boundary and the interior of the domains that you're worried about. That's kind of it. I will stop here. But this divergence theorem, I hope, is really, really nice. It's just a reminder that if the divergence is positive, we think we're sources, like we're moving out, right? It's moving out. If it's negative, it's moving in, more fluids moving in, what's more diverging? And we can calculate this by utilizing the fact that when S is closed, you know, when it bounds a volume E, we can just calculate this by the divergence theorem. And it simplifies a lot of our problems here, and not having to go through spherical coordinates, for instance, not having to go through a painful calculation of two different surfaces. This will really help us in the long run. Okay, so I'll stop there. If you have any questions, let me know, and I will talk to you guys soon.